Very powerful mathematical technique today. This is called as the principle of mathematical induction. Mathematical induction. So before we start learning the formal definition of PMI, which is principle of mathematical induction, I want you to imagine a row of 100 dominoes standing one after another. Somewhat like this. Okay. And so on, 100 of them. So what happens when one of the domino falls, like the first one, if it falls on the other? It will push the next one to fall down, which will push the next one to fall down, and so on. And thus the last domino will also experience a push and will fall down eventually, right? That is what the principle of mathematical induction all about. So whenever in maths we have to prove a statement that is true for all natural numbers, we generally perform two steps. Step 1. Step 1 is that we verify that the statement is true for the first value, or known as the base value. Verify for the base value, which is usually n equal to 1, or it can be different also, maybe n equal to 2, 3 or something, depending upon the question. This is exactly like pushing the first domino. Now comes the step 2. Step 2 is the induction step. Okay. So we assume that the statement is true for some n equal to k. Because as we have already proved that there exists some n for which the statement is true. That could be the base value, that is n equal to 1 or n equal to 10 or anything. But there exists an n for which the statement is true. So that now we can assume that the statement would also be true for some n equal to k. Maybe that k is the base value itself, or it can be anything. So assume that statement is true for n equal to k. And then how do we induce this hypothesis? Is by proving that statement is true for n equals to k plus 1. So what does it mean, my friends? It means that for every n equal to k, if the statement is true, it pushes the statement to be true for n equal to k plus 1 as well. Okay. So for, let's say, if the statement is true for n equal to 1, it pushes that it must be true for n equal to 2 as well. Okay, because we have assumed that it's true for n equal to k, and that this implies this. So if n equal to k is true, then n equal to k plus 1 would also be true. So the statement to be equal to n equal to 1 pushes it to be true for n equal to 2 as well, which further pushes it to be true for n equal to 3 as well. Okay, if the statement is true for n equal to 2, it pushes the statement to be true for n equal to 3 as well. If it is true for n equal to 3, it pushes the statement to be true for n equal to 4 as well. So this is the induction. Like if this is k, this is k plus 1. Then if this is k, this is k plus 1. Then if this is k, this is k plus 1, and so on.